excited to share my work with you. And please feel free to kind of interrupt and dive in. Obviously, my voice is so booming, I'm not used to it. I'm all too familiar with my slides, so I always enjoy room for discussion and skipping around to kind of get the most out of being together. So starting off with some disclosures, I have a company called Voyo. It's not relevant to the talk today, but methodologically related. I've done a bunch of pharma consulting before, which is also not related. Cool, but let's get started. So I work a lot broadly in cancer, and I think of personalized care as a decision problem. We have so much data per person, usually in the order of gigabytes. It's like unfathomable how much context we have. And the type of question I tend to look at is how do we use more of everything to recommend the right intervention at the right time? That's kind of the central motivation to all of my research. And it leads to work across 3 core areas I'll talk about today. One, in prediction. How do you get more insights out of the signal to understand what someone has, what they will have? How do you understand more? 2, control. What do we do about it to actually do something useful? Because it's not enough to see something coming. And finally, translation, like what's the fundamental technology of how we go from actions and policies to evidence and things we believe have done the right thing so we can learn and iterate. And I think each of these core areas are deeply exciting, and I want to share work across all of them. So to start off with prediction, where I'll spend most of the time today, where really most of my work sits. And as a motivating example, I want to kind of start off with like level sitting on like breast cancer screening, because it's kind of emblematic of how we do things across every area where we do screening. By and large, we know something. We know people above the age of 40 or like have some baseline prevalence high enough where mammograms would be cost effective. We tell them, do the same thing, you're 40, come back every year or every 2 years, depending on the guideline organization. And with every screening program, you have kind of 2 dual harms. On one side, you'll meet a lot of people. In this case, it's roughly 1 in 3 breast cancers diagnosed. They're called poor prognostic cancers, which means the treatment options are worse, the survival time is worse, like everything is just like if you known this was gonna happen, we believe we have interventions to make hair better for these people. If you saw it coming, you either give them high-risk MRI. Beforehand, we could have considered chemo prevention. For people with BRCA, for example, we've already done a lot because we see something coming, if only we knew. At the same time, many other people by number have only trauma through the screening process. Many people have biopsies they don't need and then leave the screening system altogether, which means if they actually get something a decade later, they're not much worse off. And things like both unnecessary biases, but also like the median time to go from like a screening result to knowing that you don't have cancer, at least in SF, the general, it's 40 days. And there's just a lot of like collective harm through the process. If only we knew, we should have done less. And the screening system should have been less burdensome for that. And this is kind of like the dual problems of every challenge. Like breast cancer is one example that touches many people by count. Lung cancer screening is the same way. Colorectal is the same way. Pancreatic cancer, we don't even know enough to get started. We do super severe things for people with some particular genetics to achieve neither of both worlds. And like the broad picture to how to do better is like simple. It's been, I think, simple for many decades. 1, predict, understand what's gonna happen. We need more insights. You can only, if your single variable of control is age, you're stuck. So that really is that image on the left at year 0, not the image on the right. Give me insight of the progression to the future. And then given that, do something about it, right? Because if we tell you something but we don't actually change the policy, all I've done is I've given you tidbits. So that decomposition, we'll talk about both. But I want to start off like this. It's not a new paradigm. The idea of risk modeling is also old, tried and true, and also many decades long. This risk model is older than me, and they all have the following shape: age, family history, prior breast procedures, et cetera. And this is still what runs clinical care today. And the trouble with this is that all of the work has really been in the context of finding the features, not the modeling. And all these models, despite them being the basis of current guidelines, just suck. So like the way you think of them is like, okay, well, what's the sensitivity of my classifier? Well, less than a quarter of all people who are gonna get cancer, I'm gonna call high risk before they get cancer. So that leaves room for improvement. The vast majority of people are gonna call high risk and give MRI and kind of run through this process, are also not gonna get cancer within a decade. So it's both not very sensitive nor very specific. And roughly like half of all women, we say, hey, you have dense breast, worry about it. Your relative risk is like 1.1. It doesn't make a real difference. So we've had models for a while. This is the basis of current care allocation. But from my kind of basic big picture perspective, we have a lot more than the information in those models. We have many gigabytes of data. And I want to kind of touch like, well, where are we now? And my big picture vision is the more of this we can use, the more insight we can derive to make new kinds of things possible. So I'll talk a little bit about where we are now in the community and kind of where we're going and why it's going to improve quite quickly from where we are now. Clinical care today is primarily in the world of bits. You have like maybe 60 questions, maybe 10, but like it's a questionnaire. The very minimum, and we even look at images as part of that flow, but we took the image and we asked someone to say what matters in this image, what is breast density, and you kind of map it into your risk calculator. Some of my early work back during my PhD, and this is a lot of time at MIT with Regina, was basically, well, we just take the image, learn the mapping, can you discover things beyond the human assessment? I won't belabor the technical details in this, because those new stuff I'll be sharing more about. But the richest model in the space that we developed is called Mirai. It looks at both cancer today and up to 5 years in the future. And the important thing about this model isn't the methods that I did back when we made it, it's that it works. So the blue bar here is the kind of the most detailed of the clinical models. This actually has more information than the image-based model. It looks at the image, but through the human. Many pages of questionnaires, like does the person have hormone replacement therapy, when do they have kids, how many kids did they breastfeed, et cetera. All of that gets you to a 5-year AUC, 50 to 100 of 62. Image alone gets you 76, but the most critical part is like every place we plug it in, you get the same number. These slides are out of date, but now this is, in addition to, we have a very similar model in lung cancer. Blue bar, smoking history. Look at just the asymptomatic low-dose CT, get the same kind of lift. And across both Mirai and Cybele, which is a lung cancer model, we're now across some 90 hospitals across 30 countries, across different validation studies. And so the key part of these models is not to just like, that you can, I mean, there's methods at every generation to actually achieve the improvements, but there is signal in the images that are reliably there that has always been there. We didn't invent new data. There's not some new kind of genomic assay. Yes?
Yeah, just maybe something. But this model does use the image.
Yeah, it's image only.
In the previous slide, you said that the problem with the Gale model or the previous models is that they only use age or...
They use the image through the human-derived biomarker from the image. So they look at breast density. So like a human looks at the breast. They look at the image. Then they say category A, category B. So you have to have the image to run the full thing.
Okay.
But like what that does, it actually moves the number from 61 to 62.
Yeah.
And so for a long time, there's like this big boom of like, the image adds something. Let's improve our risk model to get like a 1-point performance improvement. Yeah.
Sorry, you said it's image only?
Yes.
So you don't have the age or the...
Yeah, so we find actually you can impute the age from the image. You can impute many things from the image. There's all kind of, many things are implicit. This model can input optionally the clinical risk factors, it just doesn't make a difference.
And the family history?
It doesn't, family history you can't easily predict from the image, but if you add the full questionnaire of the tauacusic into this, it's 1 point better, and the actual downstream stuff, it's not a big difference.
So this is great, and it's great the model works, and the result is good, but obviously it's very far from perfect.
Yes.
Right. So and what you're saying is we add these other sources of data, and they don't make a big improvement. Also reasonable. Do you think what other sources of data would we need to do better?
Let me just click back. I think single bit, do you have family history in this, is not going to get it. I actually think from mammogram alone, single time points, we're very far from hitting the upper bound of what's possible. Okay. We have not even modeled multi-time points, let alone multi-time point multimodality. Like I think the natural conclusion in the space is every signal that you've collected across the last 5 years or more, which gives you like this multi-gigabyte progression. From this, understand me everything. So cancer over time, not just will it happen, but the actual type. Will you respond to this therapy or not? Like that's the long-term thing. Like you want to get something akin to like clinical world models. Like how will you progress given this full context? And we've only scratched the surface of like one time point, just the 2D, and I think very imperfectly modeled, given the constraints of what I could do back when I had access to this data. And I think the shape of it is not going to be, we're coming up with new inputs, we're coming up with new types of assays, like some novel genomic type of thing, it's going to be we just made better models off the same data. Because that's where the data is at scale.
Yeah, just about that, so genetics is not, you don't think genetics can help here?
I think it'll help a little bit. For some people, make a really big difference. Like knowing BRCA status, like there's some subset of the cancer population that can make a massive difference. Mm-hmm. I think it'll always be a smaller subset.
Like PRS or?
People have tried combining it with PRS. The difference is not gigantic.
Right.
In my mind, it's somewhat intuitive because like this is phenotypic data, and many things happen birth, and so if life matters, then you should expect it to show up somewhere. Yeah.
So this is something.
Yes.
Because do you have some polygenic score for some of your? Because that would be interesting to if you have the same as the age, that you can have some idea of the age of the person just by. That would be interesting to see if you have an idea of the PGS looking at the image, but.
So a few people have this data. They haven't run this experiment. So Vinesh Arasu at Kaiser Permanente has run a very big experiment seeing if you combine Mirai with their PRS stuff from the wisdom study, does it help? And it seemed like the difference there was very marginal, so it's not a big transformative improvement. I don't know if they've run like can you impute one from the other? Celine Vican out of Mayo ran a similar experiment, but also small scale. The trouble with some of these like new emerging modalities, like you just don't see them very often, so it's very hard to understand the way they cross map.
Or at least the familial cases, I mean, this kind of thing that...
yeah, but I think it'd be interesting.
Hidden in the image, maybe, I mean, maybe it's...
I think it's plausibly so, given that how like it gets subsumed, at least a useful part of it has to be within it. Because otherwise, like, how would you get it to be so information overlapped?
It can be more, might not be in the image.
I think it's also, the PRS versus the actual SNPs, including those are very different, right? Like the PRS is aggregating the genetics for the exact same task here. So then there must be some strong overlap there.
Yeah, I'm saying like the useful part of it. It's not the individual genes that you're playing with, but like the ways in which they come out to be predictive. If the predictions correlate, or like if it's fully subsumed by the other, then it has to be. Otherwise, it should be more complementary.
This is one type of image, so maybe I'm more in the brain, and so you have some anatomical, but you have the functional MRI. So in the functional MRI, we can see things that we can't see in the anatomical. So it's this is. So I don't know if the PGS will be here in that type of image.
Yeah, I think
that would be interesting.
Yeah. I mean, I view this as all super simplistic. There's just a lot more context than there is. I mean, like mammograms are so simple. It's just like, it's just density of the tissue in a 2D plane, and it's not even. I mean, we have 3D versions of that, but MR is a more interesting signal. You can see lots of relaxations, and like we don't have even MR models. I think the way we can make high-risk screening guidelines for MR is like you're high risk enough to do this forever. That doesn't really make sense because you should see something, you should be able to de-escalate, and if you can, then like. The basic burden to even make the guideline goes down dramatically. So there's like, I still think the space is deeply in its infancy. But, sorry. I think you went first.
Yeah.
Okay. I'm first? Okay. Is there any assumption, I mean, from practicality, a lot of women are asked to come again and again, just because they don't know. So they say, okay, come every year, every 2 years, and so on. And I'm wondering if the assumption, I mean, this by itself, just doing too many or just more, is by itself a risk. I'm asking, it's an open question. And whether indeed, the women that will get negative, they say, now it's okay, come, they don't believe. So there is this insecurity in all those measurements that I think is something, again, psychologically burden on other aspects. So I wonder if it's still very important to put, as you say, family history, I mean, what previous biopsies, I mean, other cancers in the family, whatever, something that will at least shrink down at least the prediction will be more specific, more personal.
So I wanted to disambiguate like how do you make the model better versus how do you make it easier to use. Those are kind of different things. It's like
it's two different things.
In my mind, like it is an empirical thing. Does family history help or not? Just empirically, it doesn't really make a difference. But I don't think like I'll get to this in the next part of the talk. I don't think the future of these models and the future that I would envision is like here's the correct thing to do. Everything has benefits and trade-offs, and if you could see them, you should be empowered to choose. Like, I have this conversation with my mom all the time. I climb a lot outside, I climb very high things. She would never do that. We can live different lives. And I think there's a fundamental thing there of like, are you empowered to know what's getting screened differently given your actual profile versus not? And when you don't, all you have is anxiety. Yeah?
It's more of a comment, but if there's harm to overscreening, why don't you just go for like some safer methods like ultrasound or something? I mean, the resolution is poor, but still to get there might be some signal there to identify this early on, no?
Yeah, so there is, all care is hierarchical. So like the insight to do something less invasive early to justify something more invasive is good and true. People have tried, well, what if I do ultrasound first? It's actually less specific. So it's mammograms have been kind of, in this community, found as like the cheap, lower risk version at the top of the funnel. If someone's high risk on the mammogram, then they might get an ultrasound to help adjudicate. But the intuition of like, don't go straight to surgery, right? Like don't go straight to a biopsy is always true. It's always like, it's all sequential decision making of how do I give you the best benefit for the least harm and give you off ramps as much as I can. Things like liquid biopsy stuff, like blood tests, will probably, giving good enough risk models, become a more part of the funnel. Because maybe that's more effective than routine MR, that's going to be more complicated things. I'll get back to that in PDAC. But I want to briefly touch on like how these models are being used. So like I told you the whole point is like reduce harms of late diagnosis and of screening. We're working on both. So on the late diagnosis side, let's click here. We're running our own MRI trial. So now high-risk patients by the model getting invited to a screening MR. We've been enrolling patients at UMass, now UCSF, UChicago, and UCSD. And the kind of core goal there is basically showing for the high-risk cohort, we're bringing down the absolute incidence of advanced cancer. That requires more money than we have. So the proxy goal for now is the cancer detection rate in this cohort much higher than we've seen before in other kind of screening programs. And from the very early data at UMass, it looks like that's likely to be true, but it's still early days. The other side of the picture, clicker is being slow, is how do you reduce the kind of the harms of the screening process? This is oftentimes a much faster type of thing to study because the MRI trial is years long. We ran this study last year. Core idea is, so at the SF General, I mentioned like it's 40 days to go from a screen to being told you don't have cancer. A lot of that is just workup and the natural pipeline of stuff because you have so much volume, how do you deal with it? A very simple intervention is we know at the time someone gets the image taken, in real time we know the risk of cancer. We have one person per day go through the same day slot. And so we brought down that time down from a median of 38 to 58 minutes because you can change the workflow you have this information. This is not getting rolled into just standard of care at SFGH into the future.
So
yes.
58 minutes is basically automatically, I mean, like, it sounds like
It's a human, yeah, because like if I told you read all of them in real time, you just can't.
right.
If I tell you read one a day in real time, which is all this comes out to for their higher thresholds, you can. So like,
A day would be a day. This is 58 minutes. That's
no, because very few people are actually high risk. So most of the cancers fall within the 1 a day slot.
Uh-huh.
So you'll read like 1,000 cases to find 6 cancers. So most of them actually don't need to be, like, it'll come back negative.
Yeah,
It's the
okay.
people who get elevated as like, come back for something, those people have very long workup times.
I see. Okay.
Yeah. So I think of both of these cases as like heuristic control algorithms, or like we know something, let's do something very simple to do about it, the obvious idea. But there is much more to do here. Is like how do you flexibly improve our tools to how we create policies in the first place? And I'll touch on that if we have time in the kind of second part of the talk. But the thing that makes me most excited about this kind of prediction as a modeling problem, not as a like scientific like discover the data format problem, is that this can quickly improve as just methods improve and if we have data access and scale. And toward that end, I want to tell you kind of like the thing I'm most excited about in that improvement. And this is new work from my group on foundation models for the space. Foundation models have been around in kind of many disciplines for a very long time. The things that they should theoretically do is the broad spectrum of things you might care about. So across many hundred defined in the spectrum, it should be actually better. And radiology is historically not true. Building on it should lead you to new SOTA for things that are out of distribution, different kinds of tasks. Historically also not been true. It should improve sample efficiency. So if you want to get a new performance, you should require way less samples than before. And if all the things are true, then you have something like what BERT felt like back in the day, or what like ImageNet feels like for natural image domains, et cetera. And that was kind of the goal of Pillar Zero. And I think that moment, I believe, is finally here in radiology. And hopefully I'll be able to convince you that we've made progress towards it. So to start things off, I first want to talk about evaluation, because I'll show you a bunch of numbers. And the nature of the numbers really matters. So the evaluation and the radiology viewing community for basically the entire time has been really inspired by vision question answering in regular vision. So what people do is they take screenshots off the web. So what is a radiology image? A CT scan is like a volume. It's 16 bits. It's very high resolution. There's often multiple volumes. It's across multiple phases, like pre and post contrast. So it's multi-volume, 16-bit complex. And then the output is you write like diagnoses and like the full radiology reports. That's the human flow. This is none of that. This is a screenshot off the web in a JPEG. So it's a screenshot of a single 2D frame with some like watermark on it. The question is there kidneys in this image? Which is not the clinical task. And this is kind of the thing you'll see Google evaluate on, Microsoft evaluate on, and many of the foundation models evaluate on. I will argue this is a very unrelated to actual model quality if you want to do anything meaningful. So the first step in like me showing the story is like, well, we should do evaluation of like general capability in a reasonable way. Our pitch to that is we have a long list of findings derived by attending radiologists per modality. So like in abdomen CT we have about 200, in chest we have about 90. And it's then we say like, well, is there acute pancreatitis, et cetera. And that list is defined by attendings. And we're going to probe basically for each model's representation, how can you recover these findings from the radiology reports? Does that make sense? So now we have a suite of many tasks, kind of saying what's in domain, because these things should be captured by the radiology report. All right, so this is kind of re-summarizing the same thing. There's been a lot of evaluation frameworks, all on 2D slices, all kind of QA formatted. I like none of them. Rate is kind of our own take on that, where we kind of do these questions. We do a lot of probing accordingly. OK, so with that, now I'm empowered to tell you about the rest of the story. So first I'll go through the numbers and like hopefully convince you to care. And then I'll tell you like the method ideas that were actually useful in making this happen. So on the number side, I'm going to just flash through stuff. So Pillar, the new model, we're comparing to the MedGemma 1, 1.5 actually perform exactly the same from Google. Microsoft model, MedImage Insights. Merlin from Stanford, which is a CT-specific model, and Lingshu from Alibaba, which is basically their fine-tuned Quen. To give you background, most of the community on the big tech side is just taking video models out of the box, like Gemma or Quen, changing nothing, fine-tuning it in medical data, and just hoping for the best. It empirically does not do all of that well. So on CT abdomen, across its 200 tasks, on average, here we're 8 points better. On chest, it's better. On head, it remains way better. And on breast MR, it remains way better. So like, I'll explain the kind of the intuition of why, but the kind of big picture is like we can get some reasonable large improvements across a very large suite of tasks. And to kind of restate this is like across a test set of CT abdomen, across all of these questions, the average AC across all of them is like the top win rate is here is 84%, 90, 93, and 90. So I'm hopefully convinced that like one method you can get a broad boost of performance across many hundreds of tasks. The other thing that foundation model should do should enable a new SOTA.
Does the order of question matters or?
No.
How did you select these questions? Because it's a subset of questions, right?
This is,
So for the head CT, you only have 29 tasks.
yeah, so this is the questions that our attendings on the team wrote. And right now we're actually we're working with RSNA, the national organization, to like make a bigger set of questions. I view these evaluations as like necessary but not sufficient.
Yeah.
Right, because this is not complete evaluation, right? Saying that there was a hemorrhage, whatever, it's like, where is it?
Yeah.
Right, saying there's a cancer, but like if you can't even tell me there's a hemorrhage, you for sure can't tell me where it is in the descriptor.
Understood.
And at some points, like I think this year, we will saturate these questions and it will become a poor guide of model quality. But we're not there yet. 86 is the best thing we've had in abdomen. Not nearly good enough. Like anything below 95 in this type of domain is gonna be kind of eh. So I view this as kind of like on the way, and we'll saturate it quickly. Then you want to move to like more full, flexible natural language eval, which is not good enough yet to be productive.
I think this is great. Is this kind of a public thing that basically if I have a new model, can I
Yes.
use this to evaluate?
Yeah.
Or do I need to contact you for this, or is it on the web? Like
All the code for this is okay. We're working on many things at the same time. This whole eval framework is publicly available online. It's part of the Pillar 0 release. It's just called rates and like there's code releases and stuff. Okay. You can run this on any local data set. So like if you want to say how did these models perform on, say a data set in Maccabi Sutra, you just can, because you can just run the code on the reports on this and see how these things predict. We don't have the actual uses of data publicly available because I've been talking to users about this for months now. It is an ongoing challenge they're trying to work through. We're trying to do a public leaderboard where we kind of get model submissions and have like we're calling that Project Bedrock. And there's many institutions trying to pull together data sets from to have a performance transparency. So work in progress, but the code for this is all public. Okay, so that's like kind of the check one. Other things like, okay, well, do you give me SOTA and some new downstream tasks that are not like narrowly tuned to the report distribution? So I've really told you I care a lot about lung cancer risk. Lung cancer risk is not in the report, right, because it's going to happen many years later. People can't do this. Fine-tuning in pillar 0 gives us the best lung cancer model. So we call that Cybele 1.5. Cybele 2 is going to come out later this year, and it's both way better at cancer today, but also way better at cancer in the future. Shown in the figure paper, so like in the original data set where we trained Cybele, it's better on that test set. C index is kind of the right summary measure, and then it generalizes to held out data from MGH and CGMH out of the box. So at least in SOTA and kind of like out of distribution downstream tasks. Yes?
So maybe I missed this. So are you taking into consideration any radiologist's notes on any of these things?
I'll get to that. That's the nature of the pre-training. So the pre-training itself is very vision language based, and there's some details of doing that correctly. But like the nature of the pre-training is just vision language at this stage. Yeah. So it's that's not going to be, and I'll also talk about the future direction because that's not sustainable as a source of supervision. We need to do something much more flexible. The other thing a good foundation model should do is should enable better sample efficiency, right? Like you should need less data to do stuff, otherwise everything still sucks. So first I'll start off with the baseline. So there's been a bunch of RAD foundation models out there. Like Merlin is one that was popular from a year ago. RAD ImageNet and Medical Nets are older models of the same variety. And in the purple bars, on the x-axis, I'm showing you how much data you need to get a hemorrhage detector with 95 AUC. On the y-axis, I'm kind of showing you the AUC. And if you have all the data, you'll get somewhere reasonable. But the thing that, to me, is has long been this point in the community. Like if you look at the second best model, that's actually purple's medical specific, that has not been better than kinetics, which is YouTube. So when I say like we haven't had like a true foundation model moment, like that's what I mean. It's like you pre-train on something that was specific, you pre-train on YouTube, you don't get any lift. With Pillar, we see that's not true. At the very beginning, like to compare to the SWIN 3D kinetics model, this is YouTube model, you can get to 95 using 20x less data than this. And what we see when we're training Cybele, we actually get to that performance very quickly. So it's the kind of property you'd want from a foundation model. So hopefully I've convinced you, like, the performance is something useful. So then the question is like, is it a useful thing to build on? And hopefully the answer is yes. But what I'm talking about now, like, what are the core ideas of like that actually made this model work and like the key innovations within it? There's kind of 3 ideas. All of them kind of fall within thematically taking the modality seriously. Like medical imaging is not video. It's something else. It has its own affordances, and the model should care and do something about it. The first thing is that the CT volume itself, like even within the bit, it's not a JPEG. It's not some 8-bit thing you can move to 256 and call it a day. It's actually usually 12 to 16 bits. The distribution of the pixels is actually quite long, and different narrow parts of it can show you different properties. So when a radiologist looks at it, they'll have their, I keep using this wrong. They will actually click between different subparts of the dynamic range to understand what's in the bones, what's in the soft tissue, what's in the lungs. You actually can't see it all at the same time with the way the eyes work. And if you take the full 16-bit range and just put a single linear projection to figure it out, empirically it doesn't work all that well because sometimes very narrow parts of the range are actually quite meaningful. So we have a very simple thing. We just kind of like expand this into channels upon loading. And doing that gives you a non-trivial boost in performance. And that's a very simple idea that it takes it's just not an 8-bit image. Now you would note, like if you look at the actual evals people have used, it's JPEGs on the internet. So with that eval, you would never realize that this actually makes any difference. Second key idea of like the modality something specific is actually model it as a volume. Most of the big tech models like Quen, Gemma, et cetera, model it as sets of 2D slices. It's not a 2D slice, it's a volume. To model as a volume, the core challenge is really speed. If you take a vision transformer, which is a normal backbone people use, O of n squared, so if I give you 700x more, it's just much slower. To resolve this problem, we have this model called Atlas we came up with earlier last year. Basically, we have a new attention primitive called multi-scale attention. The core idea is we're going to create windows of the input across multiple scales. So you have tokens that are very fine-grained at this scale, coarser grained at this scale, coarser grained at this scale. I'm going to do attention across all scales simultaneously. I'll show that in detail in a second, but like core idea is by changing that primitive, you can get to n log n compute cost instead of O of n squared. So to compute our volume on a single server, now it's 175x faster. So it means you can actually afford to do it. And modeling the full volume makes a difference. Yeah.
people are using like state-space models or linear transformers or things like this? I don't know if those
Yes.
apply in vision settings.
They do when we thought about it. So like if for references to those detailed comparisons, I look at the Atlas paper.
Okay.
But I don't have the slide for this here. But basically, like the thing you care about is basically speed versus performance curves.
Right, right.
And we find Mamba-based models are actually really bad. They're really fast. They're as fast as Atlas, up to like a 4K by 4K resolution.
Yeah.
But the Vision Mamba papers actually interleave Mamba blocks with transformer blocks because they actually have a very hard time transferring information.
I see. Okay.
And they do this kind of like run the 2D sequence in both ways.
Yeah.
The fixed dimension is not a very good way to propagate things. So that's O of n, but then like the communication pathway is O of n as well. Other approaches people do is like dilated attention.
Yeah.
Dilated attention is conceptually similar to what we're doing, except it doesn't respect locality. Like they do striding, but striding is actually quite silly. We think about like how we think about this information geometry of the space. And so that gives you n log n compute cost, log n communication path, which is the same as Atlas. But we do it in a way that respects locality. So practically we find that actually works way worse. So like the Atlas paper will show comparisons against Swin style model, shifted window attention, et cetera.
Oh, sorry, no, yes, that's fantastic.
Yeah, the key detail is like, idea is simple, like you have scales of features, communicate between them. Everything in deep learning is in the how. The how here is basically you do cross attention and cross scales at every block. So within a block, you do communication everywhere. There's two information flows, like from the level of scale 1, you propagate information from the top scale down. So you're cross-attending across every level. And then this kind of like lets you understand the full context from the level of like this. You talk to your neighbors and more distant neighbors who are something more coarse, more distant neighbors something more coarse. Like that's the leap from here to here. And we do a cross-attention the other direction to kind of refine this representation off of the rich information you saw here. And both of those are independently complementary to get to the full performance profile you see.
So is that kind of similar to UNet in a way?
Not quite, because UNet, you're doing this like, it's block, 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 end, end, end. This is within a block. So like it's semantically different. It's like this is a drop-in replacement for the normal transformer block. So my self-attention operation, like doing this multiple chain cross-attention stuff is actually faster than a single self-attention thing, because the sequence length is so much smaller. And then you can pack it very efficiently.
So is the top down and bottom up happening simultaneously?
It's sequential. It's like this happens and then this happens.
Okay.
But
They don't inform each other, or they do?
they do inform each other. I'll have to double check in the code, but we ran so many variants of this, so I forget which one actually works in the end. But I think you do this one and then this one. Yeah. Cool. OK, so that was the kind of key idea here. The last idea I want to talk about is like the way we do vision language pre-training. So this fundamentally pillar 0 is like a clip style model. When people do this in context of both Quen and MedGemma, et cetera, usually they'll go off SIGLIP. And the normal pattern is you're training your text encoder and your vision encoder in parallel. And the text encoder tends to be pretty small. It's like a BERT style model or like something usually the same size as the vision encoder, learned from scratch, or pre-train off of like BERT. The assumption that makes is that like that works well in web scale data, in which you have like messy images and pretty short descriptive captions that are maybe like within 100 words, and you kind of move on. Many of the clip style approaches actually have hard caps in the tokenizer for the text. They'd be like no more than 77 tokens. The radiology report is always more than 77 tokens. And it's semantically quite complex compositionally, and there's actually a lot of details in there. And so we find when you do this kind of pre-training off of like the normal open clip recipe, like you use Roberta base, even with the normal pre-training people do, improving the pre-training does not correlate all that well with improving the downstream performance. It's just a super noisy target. And this is even with fine-tuning the BERT model. It's like a standard recipe. This correlation was 0.24. We find by switching that out, like here we use an LLM, like we use Quen 8B. Now this is very asymmetric. Like the text encoder is gigantic, but frozen, you can cache it. This is the only thing that's trained live. This actually correlates very tightly. So this correlation here is 0.94. This is inspired by like spending a summer thinking the model is going to get better, and it's not getting better, and getting really frustrated. And the answer of why is the quality of the text target.
How do you extract the embedding from the LLM? In the sense that, like, for generation tasks, every hidden layer, every token, key value cache is potentially useful. are you taking a certain layer? Are you taking all of those and then running this as a
No.
projection, or yeah?
This is very simplistic. This is just the end of sentence token
Okay.
at the very end, but it's the embedding trained model. Because like, there's the...
Oh, I see. Okay. So that should help. Yeah.
Yeah, it's trained specifically for this purpose for
Okay,
retrieval.
yeah.
Now, this is still not enough. Like, this is not where we're ending because, like, we find, like, I mean, it's still an overly compressed representation. And so the things we're moving on now in pre-training for pillar 1 is not this. It's a mixed image language pre-training, because even this is too compressive.
Yeah.
Like, thematically, a lot of, like, the things in pillar 0 and what we're doing in pillar in general is, like, the data is rich, do something about it. So how do you model more of the full context, the full bit depth, the full reports, the full correspondence signal to get better representations? Those are kind of the core ideas to kind of make this thing work that enables us to get the variety of performance improvements. And I want to touch, like, this is, to me, just the beginning, because, like, for fixed data, we have not saturated yet what's possible. As part of my new hats, like, we're scaling up. The pillar 1 plus now has millions of exams. I'm hoping to get to 20 million regime within the next 6 weeks. So the data is scaling dramatically, and, like, the method is still getting much better. And so what's possible, both sample efficiency and kind of like what's possible to do in the various downstream tasks, I think will change a lot. And it's not just, we're improving in, like, this part of the access, how do you model single scan. We haven't even scratched the surface of everything you actually have, right? There's correspondences over time. There's these much richer modalities that we haven't even truly worked on. I think gives me hope that there's a long time to improve in this, like, how do you get better predictions? That wraps the kind of prediction side of the talk, but, like, there's more, because that by itself is not enough. So I want to kind of touch next on innovations in control and translation. I might skip around a bit to make sure we have time. So control, mentioned already, is kind of two-picture, predict, and then do something about it. And we already showed you 2 early heuristic forms of control. And now I want to talk about, like, learning policies as a first-order principle. And this is the focus of a paper also towards the end of my PhD, and doing this as a multi-objective RL problem. Okay, so to kind of start off, to reset the context, you tell people to do the same thing. Different people, same protocol. This person might get late-stage cancer. This person might have needed biopsies, so you want it. Your optimal is you have, like, this person gets what they would have wanted, and they could have seen it coming. This might actually have MRs in the middle. You have different frequencies depending on the person. The question is how, and what is our process to develop guidelines, and what's our fundamental technology? And I would argue the process is not good. So we have many organizations that are independent of each other. So you have NCCN, I can never say the acronym, USPTS, that one, ACR, ACS, et cetera. The general flow is they come together in a room and they'll do some literature review. They'll meet every 2 years, some every 5. Let's yell about it and pick a number. That gets you the care path we have today, which is multiple one-size-fits-all criteria. In some domains, maybe the paper they read had 50 people in it. It just depends on the individual disease. I have been in the room in which pre-seed, so I'm part of this, like, big pancreatic cancer consortium, was debating putting a response to the NCCN criteria for pancreatic cancer screening. And the flow of these conversations is always similar. It's like we see a new suggestion for NCCN, especially when there's no screening yet, like pancreatic cancer. On one hand, you say, thematically, it's like, you want to give 20 more people MR a year. I'm in Ontario. I have literally 2 MRI machines. What the hell am I supposed to do with this? I have other people who need this. This is wrong. We need to make it more strict. Someone else will say, if I didn't have this, I would have died. Why are you trying to kill me? Room goes quiet. There's some debate. There's no information. There's no data. And then we just kind of guess a number and say, OK, we approve the guideline. And that's the very unsatisfying process. There is modeling in this. The models that the US prevents, whatever this is called, uses, is all off SysNets. You take these graphical models. You say 40,000 hypothetical will be born. They're going to have mammograms that work hypothetically like this, off some data from some trial we saw maybe 20 years ago. I will run all the simulations. I have decided this is cost effective, therefore do this. Which also, there's no way to, like, bake in new discovery. You're pre-assuming the whole world. And it's like it's a full parametric approach, I think, is silly. And you also can't validate this, I keep using the button wrong, across population explicitly. So, like, there was some work, some people I know, like, the colorectal cancer screening guidelines have changed. And part of there's a big disparity of, like, when African American men might get colorectal cancer versus not. But if you model the whole world, I assume people get cancer at this age. You won't catch that. And so across many parts of this, you would hope to have something different. And this is the kind of core goal of this work. And the target is simple. It's like, OK, I have a patient. I have some information about them. For simplicity, I'm going to call it as a scalar, but it's not. I have the risk, maybe just their image and all the information. I have my policy network, we're calling here tempo. My action is like, what's the guideline trying to do? When do you come back for the next screen? And what I want to optimize for is some like intuitively weighted trade-off of like benefit and cost. By cost, I mean like, like the harm, not like just the financial value. And the core idea of the work is let's assume as little as we can theoretically do. So we have a lot of screening data implicitly in care. So I don't need to assume this person will be born. They exist. I don't need to assume that they'll get cancer. They do. And I got to see these particular observations. And to me, directionally, what is the minimum set of things I need to assume is like, well, if I give you a counterfactual for this individual person, what am I happy to assume here? And can I use that signal to then build new policies? So I'm going to assume two types of things. One is how do I estimate cost? So if I instead gave you this hypothetical trajectory, given I saw the risk here and risk here, how much more does this inherent cost of this? I would say maybe it's proportional to the number of screens, so I'll do some metric based off of that. And if you had cancer at this point, and I give you a hypothetical alternate screen here, how much benefit would I have wanted to do? So the power of hindsight. This kind of framework makes sense. I'm still assuming something. It's like the fundamental challenge in anything causal. But I want to shrink the space of assumptions to just, given some counterfactual, all the details I can get about your cancer at this time, what can I give you? And I can generate many of these metrics, so it's a vector of cost and reward. I can do people who get cancer with the power of hindsight. People who don't get cancer, it's easier because the benefit is de facto 0, and the cost function is the same. And if I can do that, I now have a signal to kind of do things across the entire population to both evaluate and learn. That kind of big picture makes sense? Cool. So then the question is like, how do we do it? There's a bunch of details here I'm going to kind of gloss over, but kind of the big picture of how we do it is the following. Like this is framed in this way. If you can put in individual actions and do this cost and benefits, now it's an RL signal. I can basically learn to basically give me, well, given my state, literally predicts me this kind of weighted cost-benefit trade-off vector. Now, it's easier to think out how you do this for a fixed trade-off, because now it's just single scalar, do deep Q learning, call it a day, move on. But as I hinted at earlier, I don't believe we'll ever agree on what this benefit trade-off is, which is good. Like, I don't think we should agree. So we can, but in this formulation, we can treat the lambda weighting as just a known at training time. So what that means is, as the inputs of the model is both this kind of state, it's also a preference vector. And given that, now give me what actions make sense, give my actual preferences over the space. And there's many good algorithms in the space. We use envelope Q-learning built by Karthik Narasimhan at Princeton. And that's like the flavor of the whole algorithm. Now, to kind of give you a sense of the experiments before I talk about translation, these models are trained in the same data. So it's all breast cancer. So it's the same data used to train Mirai, the breast cancer risk model. I'm validating it on both held out patients at MGH, but also held out patients at separate hospitals. And the shape of the numbers always looks like this. So this is a simplistic proof of concept. On the x-axis, I'm showing you here mammograms per year. On the y-axis, I'm showing you kind of the simulated early detection months. And the sensitivity analysis kind of change the assumption, how does it change? And the core thing is like, well, if I do annual screening, it's kind of age-based switch off biannual, you get a particular trade-off curve. And if you have a risk model, what you want to do is you want to push the achievable trade-off curves up and to the right. And the core property, if you wanted to do the benefit of this, well, you could do it with like a quarter or less screening. If I want to do on average annual screening, I can allocate a better ticket to get a boost in early detection. And this pattern exists within MGH, but then like I can test that it generalizes to held out places. And if you want to study it, you can just run it in your local institution. You can disagree with the assumptions, okay, just rerun the different metric and just see, well, how does that actually behave, and actually pick something that makes sense. Core idea of this work is individual trajectories that actually exist in care are a super valuable and underutilized signal within our kind of policy design engine. If we model that and assume the minimal component, which is like, well, given what I know about this cancer, what I'd rather happen with the power of hindsight, this notion is compatible with arbitrary notions of reward design and baseline models. And to me, this is a long-term sustainable approach to get the best of both worlds, both better early detection to move forward with the Pareto curve.
So
Yes?
practically, that model or that approach can be used for the US, whatever it was, or like so one of these committees to basically help them define the policy, or?
Yeah, so I view this as a capacity of policy design. What I view, like where I would like the policy work to end, is like here are models that we vetted as reasonable, and then people have agency, and we have new technologies. How do you even find your own preference? because I don't think of my world as lambda vectors.
Yeah.
You know, so I think there's additional tooling there of how do you find what you actually want, but because you're able to just choose. I think we live in a world that's like very top-down, low agency, do what we tell you, which is only reasonable we know nothing. So they actually can't have informed discussions. But ideally, you'd be empowered to choose because people have different levels of anxiety about the thing for the same level of information. And like, so I don't think it should be a one-size-fits-all, you do this. It should be personalized to risk and what you actually want to do with your life.
Yeah.
I want to note this is a more general picture. So like what I showed you earlier was like image-based risk, but all care is hierarchical, and how to even start screening is a major challenge. So there's some ongoing collaboration led by student Mikkel in Denmark. We're trying to look at the National Registry of Data, and we're looking at both. At this time, this is pre-imaging. So what I have is all the codes in the EHR. I also have the codes of your parents. Theoretically, I have the codes of your neighbors that estimate a better thing of exposome or whatever. And then I'm trying to figure out, well, is this person high risk enough to bother screening for either lung cancer, breasts, PDAC, et cetera? And I think the kind of long-term thing, how do we make screening plausible in these rare conditions? We need to say, well, what's the bridge information we already have? How do we then justify the next level of information? So we're trying to do the same thing in the context of this kind of like the graph of your codes and the codes of your community over time. That's the kind of core idea shown pictorially. Okay, so that shows that we've touched on prediction and control. Now I want to talk a little bit about translation before we wrap. I've already mentioned there's two prospective trials, right? There's this MRI trial, there's this SDA trial, but we have better models. And the trials are like actually already obsolete, and they'll be obsolete. The MRI trial for sure, by the time the thing comes out, it's going to be like MRI 3, and the numbers don't hold anymore. That's like a deeply frustrating thing, right? Because it takes forever to start a trial, it takes forever to run a trial. And our evidence framework is like not really compatible with the assumption that the model should change. And you actually get a disincentive to run a trial because maybe you should wait until it peaks, but then you don't study anything. Then we live in this kind of world where we actually rarely have AI intervention studied in practice.
Yeah, so then how do you choose your primary endpoints if they're being used, as you say, like currently outdated so quickly? Wouldn't that like throw out your clinical trial if you have to like tell your patients that this is an outdated method? Wouldn't that get it ended immediately?
It doesn't because we expect slowness. So the world has not caught up to this, but what I'm going to show you is a method to deal with this. Because fundamentally, so like I guess a key observation what's happening with these tools is that they are not themselves the intervention. They're just simply allocating intervention. So let's say we had in a world in which like an example of this is like sudden cardiac death. We have a cure. It's a surgery. You put a, I forget what it's called. It's not a pacemaker, but something to basically restart the heart if you have the event, and that can basically prevent sudden cardiac death. You're not going to give it to everybody because it's an invasive thing. You don't know who's actually at risk. But if I gave it to everybody, I would simply know the effect. I could read it out. So every one of these models is not care itself. It is not the one that saves a life. It just simply allocates care. So if I switch midway through, so the normal setup is you have like a frozen intervention, but it's not what we're doing. If I switch midway through for a better allocation function, if I'm willing to assume that basically someone who got the intervention under the prior model, if the new model agrees with the same decision that this sample is exchangeable, then I can do something. There's other assumptions that are needed to make this work, but basically where we're going is like a adaptive trial mechanism where basically like with each model generation, your fundamental agreement will actually go up over time. And reusing that agreement to make the samples needed to power the new thing go further and further down.
So have you demonstrated that yet?
This method is theoretical. It does demonstrate the rigorous thing here. We have not run the first bridge trial yet, because this thing came out, was not out yet, but we wrote this up in November. But we are switching over we ran the SDA study. This finished in October. We're going to run this now for the next MRI model. So we'll be doing this in practice.
Oh.
Yeah, but happy to dive into more depth. But the core idea here is these are real numbers of the mere 1.5 early numbers. I have 100 patients here. I already finished the trial. I now have a new model. I see for that high-risk cohort, I actually have a bit of overlap, and the marginal disagreement should actually be more enriched. Intuitively, I don't need to re-enroll the same people. Should be able to use that information. The question is, what conditions can you do so? So in the paper, I guess there's a couple things. One, this type of overlap pattern is kind of inherent to the thing. If you're both modeling cancer, both models are good, and there's better. They should agree on some of them, right? It's kind of implicit. And eventually, the prevalence should kind of go up to 100. We see across cancer, cardiovascular disease, and sepsis, this overlap is empirically high across different methods. And in an MRI trial simulation, because we're running actually this trial now with just like the MRI side, but if we had run a previous trial with a prior method, the cost would have gone down dramatically by having run the first trial. So the core idea is like, how do we change the basic incentives that actually get cheaper and cheaper to run trials, and like you can benefit from the setup, given you can fit the assumptions. Now, if folks are interested, the preprints online, core idea is like one can assume exchangeability. That implies that the data hasn't drifted, a stable population, and there's other kind of constraints to make this feasible, because you can't always do it. So like you can't do this for a drug, for example. Yeah.
So is there any concern, so I think this methodology is fantastic, to be clear, and it makes a lot of sense. Is there any concern of you're sort of overusing degrees of freedom in some sense? Like, you know, you have the initial trial, you have the sort of legacy trial participants, and you've learned something about them, and that has potentially informed some design decision of a new model, and now you're trialing the new model, but you're still leveraging the legacy trial thing. So there's sort of some overuse of information in some sense. Right? Is there any risk of statistical bias in a very sort of long tail, sort of extreme setting? If that makes sense, or maybe
I think so. I mean, I think if you're using those participants, basically the assumption here is that the models are kind of moving on their own track, which is empirically what's happening.
Yeah.
And then I'm getting new test sets, and I'm not actually using those results at all, because usually the trials are really small.
Okay.
What I'm training on is like these gigantic population models that are like, the way that I do my pre-training is kind of like asymmetric contrastive learning thing. There's no way influenced by my experience running any of the trials.
Yeah.
But I agree, like if I double use it, right, then it's not like now it's a biased estimator and we have to do something about it.
Yeah.
I think there's a lot more to do in this space. So I think like, if all the assumptions hold, then this is valid. But then how do we make it even more flexible, and how can I tell better the assumptions don't hold? Like if my population changes a lot, like if I bought a new health system and I've merged, now the population is not the same, so now this doesn't hold. But can I still get some, like is there a different formulation I can still get something? Because it's not like I know nothing. In a world in which everybody got the allocations all the time and it was actually random allocation, I don't even need to run a trial, right? Just like observational data and run it out. But you can never get that. So how do you get something useful to give you evidence as you go along?
Is there any possibility, and I'm not stressing this as a practical idea, right? This would not be something that anyone would want deployed, but you know, the models are probabilistic, and then we're making deterministic recommendations from them. You know, like if I get a risk prediction probability, and then I threshold it, and I say, okay, always 1, always 0. Instead, I could say 1 with the probability given by the model, 0 otherwise. So I preserve randomness based on the model's frequency. If we had a system like that, do you think this would make this methodology much sort of simpler, because then you can always leverage the fact that there actually is randomness, even in the prior ones?
100%, it would make things easier. Practically, clinically, you could never.
Yeah.
Because like, basically at every given trial, I'm trying my best effort, best guideline I can imagine given the models today.
Yeah.
So if I'm saying, hey, get this heart surgery,
Yeah.
it's the best thing we have, people are consenting to it, and there's kind of like a responsibility to do right. But if I think I have a better approach, I should upgrade to the best one.
No, I'm not disagreeing. I was just making sure I was understanding the model correctly.
But like conceptually, I mean, if we had random care allocation, then everything becomes really easy. But like care gets really bad.
Well, I mean, anyway, we'll talk offline.
Yeah. Oh, cool. That wraps this kind of part of the talk. Hopefully I've convinced you that to actually get to AI-driven care, you need innovation across all 3 of the spaces, from getting foresight, doing something about it, to studying in practice, because all of these spaces will move, and so you need evidence frameworks that take that into account. And if this all works, I think there's great opportunity to kind of rethink how we do screening criteria altogether and like the basic allocation of care. And with that, I want to say thank you all for your attention.
Questions? We had very interesting talks yesterday about fairness, and I was wondering if you had any considerations of fairness in this approach.
Yeah, so I didn't show this in the slides, but like probably we do all this like super global validation stuff because we understand subgroups in a more granular fashion. So we've done very simple analyses of like, does the overall model performance behave similarly across the various subgroups in different countries that we're studying? That in itself is not like the richest form of that analysis. That's kind of where things are now. The thing that we find is in every local context, the way that you would think about deployment is actually quite different. So for example, like the way we deploy the model in the collaboration in Nigeria is nothing like the way we're deploying at SFGH because the constraints are different. So that like, to me, we found in the breast cancer space, the signal in the mammogram does not seem to really depend much on this kind of other covariates of like where in the world you are or your ethnic background.
Yeah.
The allocation of care depends much more on the system that you're in. So in a system where you have no MR machines in the country, MR model is not helpful to you. And it's actually much more about how you, like...
Let's say within a single country or a single, even within MGH for different populations.
Within MGH, we see it behaves, as the best that we know, similarly across the population. So the real differences in how you think about impact is like, it's specific to the deployment.
Mm-hmm.
And so like, the way we do, like the way we would run this SFGH versus UCSF, which are theoretically the same, it's like literally the same clinicians, is different. Like the UCSF bandwidth to do this SDA thing is different than the bandwidth at SFGH. And so you wouldn't run the SDA study the same way. And like the way to do deployment correctly then actually becomes very site specific. And it's actually the constraints here is not by the population, it's by the provider. In a world in which like it has not empirically happened in the context of these image-based models, but I don't think it's going to be true long term because different populations simply will have different baseline prevalences that will behave quite differently. And so like, for example, triple negative disease has a simply much worse outcome rates. That's a different biological thing. But still, am I doing the best marginal improvement in deployment per tracker I'm deploying is kind of the framework that we take.
So if I understand correctly, so Milai, your model, just take a look on the last image, but have you considered or did you try to look on the differences between previous images? I mean, of course, there are challenges of alignment and finding maybe the difference between images, but maybe there is information in the track of changes or something like that.
We have tried a lot, and so I can give you the history of the Mirai development. I had access to data from 2017 to 2020. At the time that I lost access in 2020, I was working on exactly that. And from then to today, I haven't accessed to big enough data to make that idea super viable. You can't really align them because it's like 2D projections of a 3D blob that's actually changing in orientation and shape, and so like it's not registerable. But there is a longitudinal signal there. Practically, the challenge is that if you do learning the wrong way, it's too easy to learn it's easier to memorize the last time points than it is to learn to leverage the longitudinal information. It's a common thing in vision. So for example, like if I give you something even simpler than longitudinal comparison, I give you an MRI, let's say for prostate, I've run this experiment many times, or like I give you the T1, T2, and the GWI, and I stack them together. So I'm giving a correspondence structurally in the model. Or I give you as separate volumes, you have to learn the correspondence. But I've given you the same positional embedding. Like those two methods work completely differently. And forced in correspondence works way better. And current SSL regimes are really bad at having you implicitly learn correspondence and reasoning. This means there has to be something within pre-training of how I actually use to leverage that signal. So like done naively, it's easier to memorize the bad thing than it is to actually do the right thing. In the industry now, there's more mammal models that like, if you do something simple, you can get some small boost. Like if you just take the difference in risk scores and like, take the difference in hidden interpretations, like you'll get something. But that's not like the real thing, it's like a Band-Aid. There's a true signal there, and like we're still quite bad at capturing it, but hopefully that'll change. Yeah.
How generalizable do you think your policy informing model is? Right now, you implemented it on breast cancer screening. So now I'm just trying to go get away from CT-based screening just to other screening. We had a day about child development screening. And so if I model the trade-offs between cost and benefit, do you think I can plug in your framework of optimizing benefit and cost, of course, based on user preferences of the lambdas? How generalizable do you think we can make this framework, which I really like, to inform policymakers and help them, narrow the discussions that you were part of that, are very costly, to have something that's to have discussions that are more data-driven, but still within the framework of cost effectiveness and modeling that based on the data, not necessarily CT-based data.
Yeah, I think the fundamental requirement to do this is like I have a sense of, I see observations over time, so I can model the things in between. I have enough confidence on basically how I'm happy to make a reward function. And the other thing is I can say something about if I saw another observation in the middle of the sequence that I actually didn't see. So I didn't say this in the talk, but like the risks progression, because the input to this model is basically the risk score. This progression is pretty smooth, and so you can reliably impute the middle ones from seeing the before and after. So if you have those, then you can kind of use it flexibly. The thing it doesn't do yet, that I think would be much more interesting, is how to do hierarchical decisions. Because I give you here some very simple, it's like mammogram, when, yes, no.
Yeah.
But really, the world's more complicated. It's like, well, MR versus mammogram. And like, I'm not modeling the risk of, something else I think is a nuance that I'm not capturing here. Hard to capture within this problem is sometimes for new modalities that are really important and useful, the interpretation quality of them actually changes the outcome more than actually having it seen it. So I'm seeing this now running this MRI trial. MRI is a really powerful modality with the right person. Someone can't read the MRI does nothing for you. And like if you don't QC that part of the intervention, then you actually don't get very far. There's some new breast cancer trials in mammo showing like you can have someone read much better on the mammo. So I think, but broadly, yes, it is general. You could do this kind of any longitudinal thing. It's currently singular action. Ideally, when it generalizes the hierarchical action. And I think it's best paired with something of like, how do you QC the quality of the interpretation? Because the interpretation here is assumed to be reasonable. But if that's the bottleneck, then more allocation won't save you if people can't read the thing. So my version of the future is like, we'll have both flexible systems across everything that you see, to kind of give a higher quality bar, and then you actually need new allocations less, which would be cheaper to the system.
Very cool, thanks.
All right, let's thank Adam. Back at 10:30? 10:30.
Yeah.
Hey, we've interrupted.